brought to you by Form Systems, the leader in API and cloud gateway technology.
Okay, can everyone hear me? So my name is Nicolas Kruchten. I'm with Datacratic, and I'm here to tell you about our RTB Optimizer product, which is a predictive API. So Datacratic, we're a software company specializing in high-performance systems and machine learning. We're founded in Montreal, proud to be based in Montreal. In 2009, we have 30 employees today. We have an office in New York. And today, we have 3 predictive APIs in the market, one of which is the one I'm going to be telling you about. And we're taking basically everything that we've learned in building these predictive APIs and extracting that knowledge into an infrastructure component we call a machine learning database, which will enable others to build predictive APIs and apps. But today I'm going to talk to you about our RTB Optimizer. So can everybody raise their hand if you've ever heard of real-time bidding in the context of online advertising? Okay, some of you. So I'll have to tell you a little bit about the problem domain before I can tell you about how we solve a problem. So real-time bidding in the context of advertising works a little bit like this. You're browsing a web page. Your web browser, it needs to get an ad to show you. And when this happens through RTB, what happens is your web browser asks what's called an advertising exchange, a real-time exchange, for an ad. And then what the real-time exchange does is it broadcasts a request to a whole bunch of other players called bidders and says, please bid for the right to show this user an ad right now. So this is impression by impression, ad by ad. So these bidders respond with a bid. The real-time exchange runs an auction. The winner of that auction gets to send an ad back to your web browser, and that's how the internet determines that the ads that you're going to see. So who are these bidders? These bidders are basically a mix of advertisers, advertising agencies, and service providers to advertisers and advertising agencies. So this happens millions of times per second, continuously, 24/7 around the world. And these bidders must respond within 100 milliseconds. So this is a high throughput, low latency, hard real-time problem. And Datacratic's RTB Optimizer sort of sits behind these bidders and enables bidders to achieve their advertisers' campaign goals. So what's a campaign goal? An advertising campaign, a performance campaign, is typically what we call outcome-oriented. So an advertising campaign will be interested in people clicking on their ads. They'll be interested in people viewing videos all the way to the end. They'll be interested in people interacting with a flash object or something, or in what's called a conversion. So if you're a mobile app provider, you're interested in someone installing your app. They're interested in someone making a purchase on your e-commerce site, signing up for a service or something like that. So 2 typical use cases are one in which an advertising network, which is kind of an intermediary in the advertising world, has sold an advertiser 1,000 outcomes for $1,000, let's say. So now that advertising network needs to go out into the exchange and buy 1,000 outcomes for less than $1,000. Another typical use case is an advertiser has a budget, say $1,000. They want to spend it, and they need to get as many outcomes as possible. So mathematically speaking, this boils down to one of 2 things. You're either maximizing profit or you're minimizing cost per outcome, which are 2 sort of interrelated objectives. So Datacratic's RTB Optimizer, it's an HTTP API, pretty simple. The client bidder will relay bid requests to the API, and the API tells it how to bid. The client bidder is basically responsible for managing the connection to the exchange and for managing all the information about the campaign, which ads to show. So our customer basically manages the relationship with the advertiser. We're a service provider. This API handles hundreds of thousands of queries per second for hundreds of campaigns. And the API, in response to a bid request, will tell the client bidder which of the hundreds of campaigns it manages should bid and how much. And in order to do this, you also need to give the API a real-time stream of outcome information, and you need to tell it what the campaign goals are so it can do its optimization. So this is basically what I've told you about our system today. I'll be building up this diagram as my little presentation continues. So something I want to make very clear in this presentation is that this is a predictive API that learns. Datacratic has no proprietary data set. When you first integrate with our API knows nothing. This API will basically learn from scratch, or it can learn from scratch, from the bid request stream, everything that it needs to know to figure out what works for any given campaign. So the way it does this, what's the data that we're using in this predictive API? Each bid request contains a number of features. So there's contextual features. For example, which website is the ad about to be shown on? Where in the site is it? What time of day is it where the user is? What shape of ad is this? There's also features about the user. For example, where the user is based on their IP, what browser they use, what language this user speaks based on the language settings of their browser, how many impressions have we already shown this user for this campaign, all things that matter. And then finally, the upstream bidder, the customer, can inject additional data into the bid request stream, saying, well, we know this user is interested in cars, or we know this user has purchased from us before. All this information goes into our predictive model, and as I'll be explaining a little bit later, we train machine learning models on this data in order to produce optimal bids. And our API can also provide insights into which of these features are driving the most performance for each campaign. And it sounds a little silly to learn from scratch every single time for every single campaign, and it is. So the API allows the customer to reuse learnings from previous campaigns and just sort of update the models for future campaigns if that's appropriate. So in order for me to explain to you how we actually compute a bid, because I'm going to try and, within the bounds of time, to be as open and transparent as possible about how this works. That's why I'm here. I need to tell you a little bit about second price auctions. So if I say the word auction, maybe most of you are thinking about the dude that speaks faster than me with a hammer. He'll say, can I get 5? Can I get 5? Can I get 6? Can I get 6? Okay, 7. Sold at 7. So this is the first price auction, right? If you bid $1 and I bid 2, well, I win, and I need to pay $2. Turns out that real-time bidding uses a different kind of auction called a second price auction. In a second price auction, if you bid 1 and I bid 2, I still win, but I only need to pay 1. So this type of auction has been chosen for RTB, for the RTB context, and for a couple of others as well, because the optimal bid for any given player in an RTB auction is to bid the expected value of winning. And I'll give you a quick sort of hand-wavy proof of that. If something is worth $2 to me, then there's no way I'm bidding any more than $2. I think we can all agree that if it's worth $2 and I bid more, I might win at more than $2, so I'm not going to do that. But there's also a strong disincentive for me to bid less than $2, because if it's worth 2 and I bid any less, and you bid between me and 2, say I bid 150, you bid 175, I'm basically left 25 cents on the table, because I could have had something for $1.75 or €1.75, sorry, that I was willing to pay 2. So essentially, in the long run, it is always optimal to bid the expected value. So that doesn't really simplify our problem very much, because this is still kind of an economics problem, and I need to go one more step to turn it into a predictive problem that I can use machine learning for. So basically, the core insight is, this is why people don't buy lottery tickets. This is basically the only equation I have in my deck. The expected value of any sort of process is the payout times the probability of getting the payout. So even though sometimes the lottery payout is very high, the probability is usually vanishingly small, and this is why it's not usually worth it to play the lottery. So in the context of online advertising, if a client is basically if you've sold 1,000 outcomes for $10,000, then your expected payout is $10, and the way you can bid, your expected value for any given bid request is $10 times the probability of getting that payout, times the probability of conversion. So this is how we translate an economics problem into a prediction problem. Now we can use machine learning. And one thing of note here is that we actually need an accurate prediction. It's not enough to get a score. We're not doing typical classification where we set a threshold and we say A or B. We actually need an accurate prediction, an accurate probability, which is a sort of an additional wrinkle in the machine learning problem. So basically now here's what I've told you about our RTB Optimizer. So bid requests come in the top, we compute the probability of outcome, we compute the expected value, and we return the bid. I haven't told you a lot about how we use the outcomes. So any machine learning problem, you need to collect some data. I've said that our API basically learns directly from the bid request stream, so you don't provide it a data set up front. As we know in machine learning, in order to compute the P of x given y, well, we need a bunch of y's, and we need to know if they are x's or not. In this context, we need a bunch of bid requests, and we need to know if those bid requests have led to the outcomes that we care about. So the way that the RTB Optimizer does its thing is that it decomposes campaigns into strategies. to meet the campaign goals. So there's two strategies that are of interest here. One is the probe strategy, which basically bids fairly randomly in order to collect data. So it's kind of probing the world, sampling the world, looking for signal. And the more interesting strategy is the optimized strategy, which bids with the expected value. So basically, throughout the campaign lifecycle, when you first start a campaign, if you haven't specified any previous data that we can use, a probe strategy will launch, and it will start sort of sampling the space until enough examples of the right kind, enough positive examples have been found in order to train a model, at which point a model is trained, deployed, and we start bidding with an optimized strategy. This is fully automated. There's no humans in the loop here, except if there's some sort of training failure or bias detection alert that goes off. And models are automatically retrained as examples keep flowing through the system. So this is my slightly more complex flow diagram. So bid requests come in at the top. They either get routed to the probe or to the optimized system. If they get routed to the probe, we just bid fairly randomly. And outcomes come in through the Outcomes API. So as we're probing, we're buying impressions, and we're finding out, are people clicking? Are people installing the app? Are people viewing the video? This is streaming in real time. When enough examples have been gathered, we train a classifier, and we can start computing probabilities. So an interesting thing that we do is we never actually stop the probe strategy. We always need a control group in order to evaluate whether our system is doing well or not. This is sort of basic science. And we also need a control group that's unbiased to do further trainings of the model. If not, we risk what we call a filter bubble, where basically future generations of our model are basically learning from the output of previous models. And they're just going to kind of hone in on a very limited subset of the sample space. So we need to kind of keep on sampling a diversity of possible bid requests in order to sort of adapt to changing conditions in the market. So basically the way this goes over the long run is that bid requests, when they come in, are randomly routed either to the probe or to the optimized strategy throughout the length of the campaign. But the bid requests are routed to the probe less and less often over time. And finally, we use this ongoing probe data. Every time we retrain a model, we simulate the performance of that model we basically backtest over the historical data that we've collected from the probe. And if the model doesn't beat the baseline or doesn't beat the previous model, it's rejected and not put into production. Again, this is fully automated. So we keep on probing in order to retrain, but how can we actually learn in real time, right? This is real-time bidding. It's got to be real-time learning. So the way we've addressed this problem is sort of a hybrid online-offline mechanism. The classifiers we use are very simple classifiers. They're back-generalized linear models. But we feed nonlinear features into them that we generate with statistics tables. So I'll give you an example of a statistics table in a minute. But the general idea is that we can periodically retrain the classifier every couple hundred or every couple dozen positive examples, but we can continuously update our statistics tables in real time. This means that if a user clicks or converts, that information is incorporated into the very next bid request within milliseconds. And this is basically the way we handle the real-time stream and adapting to changing conditions, even in between retrainings. So here's an example of a statistics table that we use to generate features. So I've got two little samples of different tables. So the table for the browser will have a bunch of different buckets for each browser. So let's say a bucket for Chrome and a bucket for Firefox. And the table for website will have far more websites than this, abc.com, xyz.com. Within the statistics table, we record the number of impressions that we've shown, so the number of bid requests that we've won, and the number of outcomes that we've seen. And then we can compute ratios. The outcome rate basically is the number of outcomes divided by the number of impressions, and we can smooth that so that if you get kind of one outcome for two impressions, you don't all of a sudden think this is the greatest source of outcomes in the world. So we compute something like a 95% confidence interval lower bound on that rate, and that is what we use to generate features for our model. So essentially, if you get a bid request coming in, which is from a user using Chrome on abc.com, then part of the feature vector, which will be fed into the GLZ, is the corresponding values in the right-hand side there. So this is updated in real time. Every time we show an impression, we increment the counter in the relevant bucket. Yes, the website on which the impression is about to be shown. So within the context of the auction, you're bidding for a right to show an ad on this particular page on this particular site right now. So this is sort of my final my final system diagram. I basically split this up into real-time and batch. So real-time is in green, batch is in purple. Bid requests come in. They're randomly routed either to the probe or the optimized stack. We feed the request through the stats tables to generate features for the GLZs. We compute a probability. Then we feed it to the expected value model, which uses the campaign goals to compute the expected value of this bid request, and that's the bid. When outcomes come in real time, they update the stats tables, and they also update a data store, which we're constantly monitoring for whether or not we have enough examples to warrant a retraining. New models are trained and pushed into productions if they clear the sort of simulated backtest criteria. So as with any high-performance system, implementation details are basically everything. You mess up one thing in a high-performance system and it doesn't work. So this system handles hundreds of thousands of requests per second. It has a 10 millisecond latency, even though we're generally allowed about 50 milliseconds. We target much lower than that. It runs 24/7, and to date, it's a little hard to estimate because all I have are aggregate counts, but we've probably made about 1 trillion predictions with the system for all our customers combined. It's a distributed system. It runs across multiple machines, multiple cores. It's all written in C++. There's a little bit of glue code in Node and Python. And the system itself is capable of running on AWS, although the real-time portion of the stack can also run on-premise. All of our data is stored in AWS, and all of our training happens on AWS. What we do is we basically schedule our training jobs to run on the Amazon spot market. So we wait for the price to come low enough. Then we run our training jobs. If they're interrupted, they're just restarted. And that's where we run all of our training and backtesting. We're big believers in open source. We use open source. We contribute to open source. So you can check us out at opensource.datacratic.com. 3 things that you might find useful there. One is RTB Kit. It's basically a toolkit for building bidders that you can use to bid on the exchanges and eventually to connect to the RTB Optimizer. It's also the underlying technology of RTB Kit is what we use to build the RTB Optimizer, so that's fully open source. All of our machine learning algorithms, we have sort of in-house implementations, which are also open source. JML, Jeremy's machine learning library. Jeremy's our CTO and founder. And I've just highlighted Star Cluster. We're a contributor to the Star Cluster project, which is a way of sort of managing an open grid engine on the Amazon spot market. So, does it work? I suppose any machine learning person really cares about the classifier. I could share ROC or calibration curves with you, but I don't find those particularly informative in the absence of context. Does the optimizer work? It does. It provides an 80% reduction in cost per outcome against a reasonable baseline, basically a manually optimized campaign. But what's most important for us is the success of our customers. So can our customers succeed with it? The answer is yes. Our customers that use the Datacratic RTB Optimizer to power their optimized bidding have seen up to 25% month-over-month growth in their business, and we consider that to be the best measure of our success. Thank you.
Brought to you by Form Systems, the leader in API and cloud gateway technology.